Mm, thank
Okay,
you. Thank you
go ahead.
thank you
Go
for
ahead,
joining.
Dr. Kim.
Yes. Thank you for joining this presentation. I'm Kiwook Kim of KISTI, and I've been presenting in the APRP working group regarding wireless and data center communication technologies since before. Today, I am going to introduce BBR and BBR sweep on advanced TCP congestion control technology developed by Google. Our focus will be on how BBR Swift optimizes data center performance through improved congestion management techniques. This is what I've been researching with interest these days. Please understand that I don't have deep knowledge on this topic. Now let's begin. At the last APIP session, I introduced you the index project of KISTI. Explained the concept of data exchange node by comparing it with the existing internet exchange system. In the left figure, the large-scale data traffic, such as raw data for AI training, causes significant bottlenecks when passing through IXPs, leading to congestion and reduced service quality. On the other hand, in the figure on the right, the data exchange nodes do not handle regular internet traffic unlike IXP. Instead, the data exchange node links various data networks directly to ensure fast and secure data transfers. This is particularly crucial for research data, which can be very large and sensitive. Another advantage of this structure is that it can be physically separated from the internet network, thereby reducing the risk of security attacks. KISTI's infrastructure includes the establishment of regional nodes across Korea. We completed the pilot nodes in Busan and Seoul metropolitan area. In particular, Busan node is located in Busan Cable Landing Station, where most of the international submarine cables entering Korea are connected. So it is expected to be used for many global research partners such as APRP Group. As I said on the previous page, I am working on communication networks between data centers these days. So I'm personally studying what technologies are used for internal and external communication in data centers. One of them is the TCP congestion control algorithm for the data center that I'm going to explain today. As you are well aware, various TCP congestion control algorithms are continuously studied for over 40 years, and some of them are reflected in new implementation versions of TCP, or some others used in specific applications. Wikipedia says that there are this, this is right side any TCP congestion control algorithms if only the famous ones are selected. Of course, I don't know all of these. I'm only going to cover the PBR and PBR Swift technologies applied to Google Cloud. To start, let's define what BBR and BBR Swift is. BBR is one of the latest TCP congestion control algorithms developed by Google's TCP BBR team, including the renowned engineer Van Jacobson. Since introduction, mm, since the introduction of its first version in In 2016, BBR has undergone significant updates with BBR2 released in 2021 and the latest version of BBR3 in 2023. And while most of other congestion control algorithms are loss-based, which rely on packet loss to detect congestion, BBR uses model-based congestion detection similar to TCP Vegas. It uses bottleneck bandwidth and round-trip time to measure and adapt network flow dynamically. I discussed this model-based and loss-based congestion control in next slide. PBR is already implemented in widely used platforms, including Google Cloud Platform, YouTube, and also there is a PBR implementation for Linux TCP since Linux 4.9. When implemented at YouTube and PBR version 1 build on average of 4.4% higher network throughput and up to 14% in some countries. BBR Swift is a branch version of BBR version 3, which optimized for data center networks and high performance environments. It uses network RTT except for receiver delay as the primary congestion control signal to ensure fast response time. Mm, This graph shows the difference of loss-based and model-based congestion control mechanism. Mm, The BDP is an abbreviation of bandwidth and delay product. Imagine a network as a single physical pipe, then the network bandwidth is the thickness of the pipe, and the network delay, round trip time, is the length of the pipe. Then the BDP multiplied by bandwidth and delay becomes the volume of entire pipe. That means the capacity of the network link. In 1979, Leonard Kleinrock proved that the point A in the graph is the best operating point to achieve maximum throughput with minimum transmission delay. In other words, for optimal performance, we need to adjust the sending rate so that the amount of network usage is at point A. If we push packets into the network beyond that, beyond the A, then head toward B, the packets are buffered into the network, resulting in higher network delay. Existing loss-based methods do not respond to congestion until they reach point B, and the network queues overflows, causing the packet losses. In data center level networks using 100 gigabps or more backbone network recently, one packet loss makes big failures of data transmission, so the packet loss of this loss-based mechanism is a big problem. Another problem is that the loss-based mechanism presupposes that the network of full buffers. If there's queued packets in network, it causes the response delay. The longer network response time is a big problem for web-based services such as YouTube. So for minimum response time, we need to make the network queued packet close to zero, close to the A point. For this reason, it can be understood that Google is developing a model-based method for data centers. Model-based congestion control ensures that these optimal points are maintained without causing packet loss. And the various versions of BBR have different ways of calculating or measuring this BDP point. This page shows the BBR core mechanisms based on BBR version 1. BBR relies on two main metrics, bottleneck bandwidth, BTL, BW, and minimum round trip time, ITPROP. Bottleneck bandwidth represents the maximum amount of data that can be transmitted through the network without causing congestion. And 그 minimum round trip time indicates that the shortest round trip time reflecting the network's baseline delay when there is no queue buildup. BBR estimates the bottleneck bandwidth, available bandwidth by continuously tracking how much data is delivered successfully over time. It calculates delivery rates by measuring how fast acknowledgements are received from the receiver. And the minimum round trip time, BBR records the lowest round trip time observed for over a specific period, assuming this reflects the network's true propagation delay. This minimum RTT is periodically refreshed to adapt the network changes. So, for congestion control, BBR uses this formula, but this formula multiplies battle bandwidth and round trip. 음, 음, 아. BBR uses this formula, multiplies battle bandwidth and minimum round trip time to adjust its sending rate to match the network's capacity. If the measured ITT exceeds minimum minimum round trip time, indicating the network congestion, then BBR reduces the sending rate to avoid overwhelming the network. Then at startup, the the algorithm quickly increases the sending rate to probe for the maximum available bandwidth. After identifying maximum bandwidth, BBR goes to the drain page. It temporarily reduces the sending rate to empty any existing network queues. Then the BBR periodically tests for better bandwidth availability by briefly increasing its sending rate. And BBR occasionally lowers its sending rate to confirm the current minimum ITT, ensuring its calculations remain accurate. By continuously cycling through these pages, BBR adapts dynamically to network conditions, maximizing throughput while minimizing congestion. Mm. 2 years after BBR version 1 came out in 2016, several papers from 2018 began to present some problems of BBR version 1. These include fairness issues and when competing with loss-based congestion control algorithms such as Cubic, which could lead to unequal bandwidth distribution. So BBR version 2 attempts to deal with the fairness. Compared to BBR version 1, BBR version 2 includes two additional information to each model about packing loss and information from explicit congestion notification. Instead of solving the fairness problem, BBR version 2 is known to perform slightly low throughput compared to BBR version 1. In addition, several performance problems and bugs are reported and BBR version 3 appeared to solve them. And finally, BBR Swift, which uses RTT-based congestion detection signals, was released to ensure fast response time. 음, let's compare how BBR and BBR Swift operate. BBR Swift builds on BBR by incorporating fairness mechanisms and more responsive adjustments based on real-time network conditions. To this end, Swift uses explicit congestion notifications as a congestion signal and uses it to monitor RTT instead of estimate it. So the sending rate reflects more reflects more immediate RTT changes and congestions instead of the maximum bandwidth value. Let's look at the key performance improvements achieved by BBR Swift. First thing is fairness improvement. Unlike traditional congestion control algorithms that rely only the packet loss, BBR Swift also uses explicit congestion notification signals. This allows the algorithm to detect and respond to congestion earlier, ensuring smoother traffic flow. BBR dynamically balances bandwidth usage among competing data flows, solving fairness issues seen in previous BBR versions. It prevents certain connections from mm, monopolizing network capacity, ensuring equitable distribution. The second thing is network performance enhancement. By reacting promptly to network congestion signals, BBR Swift minimizes transmission delays. It- This makes real-time applications like video streaming and online gaming more seamless. And BBR Swift continuously proves the for available bandwidth and adjusts its sending rate accordingly. This results in higher overall network efficiency and reduced idle capacity. Third thing is data center optimization results. During Google's data center test, BBR Swift reduced the packet retransmission rate to only 0.053%. This means fewer data packets were lost or needed to be resent, improving overall throughput. PBR Swift achieved a fairness index of 0.9556, indicating highly fair bandwidth sharing among multiple network flows. Mm, Currently, BBR Swift is undergoing internal testing with Google's data centers, and Google has integrated the BBR Swift into its internal data traffic management system, where it has shown significant improvements in reliability and network efficiency. And BBR Swift is being considered in the Internet Engineering Task Force (IETF) standardization process. This effort will enable its adoption as a universal TCP congestion control standard for data center links. Google plans to release the BBR Swift source code, allowing developers, companies, and researchers to integrate it into their network systems. I think the BBR Swift has the potential to extend beyond data centers to cloud services, enterprise networks, and even consumer-level internet applications. To conclude, BBRC represents a major advancement of TCP congestion control technology by focusing on precise network measurements like Bartlett bandwidth and round trip time. BBR Swift addresses the limitation of earlier versions and offers a more reliable and efficient way to manage data traffic. I'm interested in data center communication, and I'm going to follow steadily on BBR and Swift as one of the technologies involved. Thank you. Thank you very much for your attention.
Thank you for Dr. Kim. Anybody question about that? Yes, audience.
Hi, I'm Francis, and I'm very interested in what you say about BBR Swift. Have you heard of Ultra Ethernet, which is also for data center, and especially designed for especially AI data centers, where it actually can go, the transmission can go on two different paths at the same time. You know, it takes multiple paths to reach the destination. Do you think that will be a better way rather than everyone following one path and causing congestion? So now it's taking multiple paths instead of single path.
Mm, mm, I don't know much about Ultra Ethernet. Mm,
It's okay. The other question is I played with BBR version 1, and when we tried it between Singapore and Finland transmission, the performance wasn't good. You know, it was no better than the other TCP loss-based congestion. We run with about 6 to 8, 4, 6, 8 parallel sessions, and to try and push as much as we could. But there was a limitation because of the learning. It drops, so there's so-called try to empty the queue, and then comes back up again, and it didn't quite reach the peak. Yeah, just sharing. Yeah. Andrew, I can see you wanting to say something.
Hi, Dr. Kim. It's Andrew here. Did you need to do that tuning on both of the nodes that you were using, or were you using one of the default congestion controls on the receiving end?
Pardon?
Yes, I can reply. He just is a start stage, and he mentioned before, and he want to deploy the BBR algorithm, and the prototype is inter-data centers in KREONet is very small size. So I think he's still more the research and studying for the when you cast.
We would be very interested to hear what your results are, because we have two data centers very close together at NCI.
Yes, that's very good. And the single LAN and the NCI and your experiences, your interesting is the more helpful to us to how to deploy in Korean BBR Swift.
If you would like a test site remotely, I'm happy to set up a node for you to try in Australia.
Yes,
Let's long distance.
yes.
And you need to do some phasing so that they don't fight with each other.
Yeah.
So phasing is really important.
Yeah.
That's good. Yeah.
So you can hear us. Yeah.
Okay. Thank you. It's time is go fast. And thank you for Dr. Kim for your presentation. And the next speaker is Professor Susumu Tate, and as on the desk. And he came from Osaka University, and the director of this Osaka University HPC Center, and he also deployed this high bandwidth transmission or something like that. Today he also introduced his the main project Onion. Okay, a little bit wait.
It's okay.
Yes, it's
Yes,
off.
yes, yes. Hello, I'm Susumu Date from Osaka University, 200 kilometers far from here. And 2 days ago, so I was fine, but now I have a problem in my eye. Sorry for this time. So anyway, so let me start with my presentation. My presentation. So this title was kind of given by the Professor Moon. So I used this. And today I'd like to talk about our university's project towards the kind of the convergence of HPC and AI. So the AI era. So the people have to use a lot of data for computation and computation. So from that request, I'm working for the building of the data infrastructure for our campus, and for such infrastructure, currently. I have been working on the development of the data aggregation infrastructure named Onion. So Onion is short for the Osaka University Next Generation Infrastructure for Open Research and Open Innovation. This is the name of the infrastructure. And so we don't have any money for the building of the data infrastructure itself, because so far our computing center focusing on the supercomputer system only. So that's why in the last procurement of the supercomputer system named Onion, so we have built the functionality of data aggregation infrastructure into the procurement of supercomputer system. And you can see the right bottom of the slide. So that is you can see the Onion name. And actually, we just modify or change or upgrade the data storage on the supercomputer system, so that the users of supercomputer system and non-user of supercomputer system can enjoy the data access to on our infrastructure. And this slide shows a very basic overview of the concept of Onion. And so far, the supercomputer system is just provide the storage system on the supercomputer system just provides the high performance I/O. So many users just expect higher read access and higher the write I/O access. So, but now, so in the era of the AI and the HPC, the people expect the kind of aggregation functionality of the data to the supercomputer facility. So that's why I'm trying to I try to add the functionality of getting data from the several data sources on campus, such as the IoT devices and scientific devices. So in our campus, there are many scientific devices like telescope and microscope. And nowadays, many people are excited about setting up the IoT devices and get the data from such devices. And as a result, so they want to analyze the data on supercomputer system for AI or HPC. Yeah, this is a concept. And anyway, this is so the concept slide. And this is so the what Onion can do. And so basically, the current we have already prototyped the Onion data aggregation infrastructure, and as a result, so now our campus can ready for the getting the data from the data from scientific measurement devices, and also from the IoT devices, and and also the now after the immediately after the computation on supercomputer system, the user can share the data on, to share the data to the international collaborator researchers, and also they can combine the data. Users can combine their own storage system in their laboratory or in maybe house to the Onion data aggregation infrastructure, and also now user can access the data through the intuitive user interface. Even if the user don't have detailed knowledge on the storage system, so this is the and for such for realizing the concept of Onion, so we have combined 3 different types of the storage solutions: Nextcloud as online storage, and exascaler, DDN exascaler as parallel file system, and hyperstore, Cloudian hyperstore as object storage. So we combine these 3 technologies using the AWS S3 protocols, and we now anyway, so prototype like this. And now from this is this slide shows the over perspective. This slide shows the user view of Onion. So now users supercomputer system can enjoy the single disk image of the several Onion aggregation infrastructure. Now through the web intuitive user interface, user can access or use the data on the parallel file system and object storage, and maybe the data storage on the laboratory, and of course currently the now campus users are trying to connect the scientific devices to the Onion, so that the data can be synchronized or automatically stored to the Onion data infrastructure. And this is one of the project, and we have the core facility center in the campus. The core facility center is in charge of the management and operation of the scientific measurement devices. Such devices are expected to be used by the researchers in Japan, and so that means that such devices are not available not only to the researchers in Osaka University but also Japan. Okay, then so far the people are using these scientific devices and then bring the data to their own laboratory using the USB or hard disk, and they are expected. They want to have more elegant way to bring the data, and also even for the users on campus now, and still users are bringing the USB or hard disk. That is the problem. But after the Onion, so now they are trying to develop they are now they have developed a prototype of the data delivery system from the scientific devices to the Onion. And now they are backing up the data every day, and maybe after the analysis, so they can be they try to preserve the data on the NII, so Japanese Research Institutions research data management system for the research reproducibility of something. And anyway, this is the Onion. So. And so today's talk is focus more on the red onion. So red onion is what is red onion? So red onion is research enhanced onion. So this is a new project, and so again, so now people are using trying to use the Onion for the data aggregation. But the problem is always performance. So now, our Onion system rely on the campus network. Campus network, the campus network is used for the daily lecture or class or online things, and also email. Many traffics are there, but so we cannot use up such bandwidth of such campus network. And so many people are now complaining about the performance of data transfer for data aggregation. And so that's why now we have decided to do, make another infrastructure for data transfer. And so this is a very basic view of the Red Onion project. And the right top in the slide is our center, computing center. In computing center, there is a supercomputer system and the Onion data aggregation infrastructure. And so that on campus there are many research institutions and departments which generates a lot of data every day. So medical school also, the hospital also, and yeah, many centers are there. And now we are now trying to set up or establish the dedicated network from our computer center to such departments. And we try to get the data. We can aggregate the data generated on each department to more efficiently to Onion system. That is the plan. And for realizing such a dream, so now we are now designing the system. And so this slide is a very basic design of the Red Onion. So anyway, so we'd like to send like this the data. Okay. So now I'm as a computing center would like to provide very intuitive intuitive user interface for the users. So user GUI is something like this. So just asking for the destination. So I'm in the department or research institution, and maybe from somewhere, and which kind of data the user want to do. So now I'm trying, and the data is always going to our computing center and to the destination center. That means we can if user want to store the data on our computing center, the data can be sent to our Onion data aggregation infrastructure. This is a very basic view, and so for realizing this, so performance we have to think about. So even if we set up the 100 gigabps network in dedicated manner, performance always is not always conducted. So that's why we want to make sure that the performance can be achieved. So sorry, it's okay. Yeah, and so for the purpose, so we did in the demonstration using the several technology in supercomputing 2023. And at the time, so we couldn't get the performance, expected performance, we couldn't. So, and we used the Japanese company's technology, so ARCIR, the network transfer technology, and we tried to get 100 gigabps net bandwidth. So the experiment network is actually we use the JGN Japanese NYCT's provided network, but the problem was from between Denver and Osaka, so we had to use two 80 gigabps network, and but we expected we could get the 100 gigabps throughput on such environment, but the actual result was only 40 gigabps net bandwidth, and in the case of disk-to-disk network. So actually we tested the memory to memory. So memory to memory measurement data transfer was okay, so almost 100 gigabps. So disk to disk is always a problem, and as a result, so we try to improve the performance, and network transfer is something like this. So the data is actually cached memory, and CPU actually send to the another way, and after the caching again to the OS buffer, and it's the same way. And so there are several bottleneck points. So memory bandwidth bottleneck and OS caching bottleneck and sorry, I cannot see your bottleneck anyway NE. And so actually, we after the result of the supercomputing 2023, so we collaborated with the Japanese company NEC and Clearing Technology, providing ARCIR, and also the storage vendor DDN, so the data direct network. And we tuned actually the operating system a lot, and we tried to multi-threading of data transfer so in the on the right top side, and so we remove the bottleneck of the memory operating system side, and as a result, so again, so we tried. So again, in supercomputing in 2024, and originally we planned to do this demonstration on the different two types of the environment. Left side is from Japan to the United States, and right side is only in the United States. So Los Angeles to the venue to Los Angeles and again back. So I tried, but unfortunately the right side demonstration couldn't do that because of the network problem. Anyway, so we tried this Japanese side, and as a result, so we could get the almost 100 gigabit network, the bandwidth to the on the using the technology which we have achieved through the collaboration of DDN, NEC, and clearing technology. And so anyway, so actually we tuned the direct I/O and asynchronous I/O on the operating system. And anyway, this is the result. So now we are ready for providing this technology to the campuses. And based on the success of the supercomputing demonstration, so we are now center part. We are now we are now installing the center part of this red onion. This part of red onion, and this is the actual product solution. And we are using the NVIDIA Mellanox the switch. So I think this is a 200 gigabit network. And behind the network, so we have set up the we are now installing the 4 DTN nodes using the ARCIR technology. And after the DTN servers are connected to the DDN provided storage solution, so SSD parallel file system. And virtualization as virtualization infrastructure, so we have we are installing the 3 physical computer nodes. So these computer nodes are expected to be used for the for the job scheduler, which controls the data transfer sequence, and also the authentication part. So this is actually backup part, and we are now preparing. We are now discussing with several. We are now talking with several research institutions and department on campus, and if we have succeeded negotiated so the introduction of the red onion, so we are going to install the DTN on remote side, and so after that, so anyway, so we can like this. So now this is a kind of my dream. So now we are trying to aggregate the data aggregation, data infrastructure and computing infrastructure, and now trying to combine the data high-speed data transfer services on this infrastructure. And then, so we'd like to promote and facilitate the HPC and AI research on our campus. And this is a very basic view. So we are now trying to left top part of the left top part. We are working on the top left part of the work, so named red onion. And now we are going about to aggregate the data from the automatically to the onion very efficiently. And so on top of the onion data infrastructure, so our computing center are providing supercomputer system and cloud infrastructure. And also, after the computation finished, we are library or university URA supporting for the data preservation, reproducibility of data. So for the open science era. So this is the view. And so thank you so much. This is a summary. So we are now planning and installing the red onion. And so now we are working there. And actually, in my feeling, so technologies are not problem. So technologies are ready now, but business model for the sustainable operation of red onion is now problem. So for maintaining operation of the red onion, so we need to pay money for the companies for support. And now we are designing the business model. Thanks so much.
Thank you, Professor Tate. And with the time was delayed, and I wanted the next speaker, and I changed this speaker, the fourth and the fifth, and Vincenzo Capone came from this Jeonghoon in Europe, the research network, and he talking about navigation through this data storm, and please is within the 15 minutes. Okay, thank you.
Okay, thank you very much. And as Jeonghoon say, I come from GEANT, which is the European Association of the NRENs in Europe, and also the institution that manages the pan-European backbone infrastructure for the RNE community. The subject of our chat this morning is about the evolution of the utilization model of our infrastructure from the user community, seen from the point of view of someone that basically works with this as his daily job. Let me just start with showing you the mission of GEANT, and in particular, I want to focus your attention on the second bit, which is the mission of delivering an information ecosystem of infrastructure and services. This will come back, in a few minutes, and to give you the full context of what I'm about to explain. A few years ago, the GEANT community has embarked in a journey to refresh their strategy entirely. So they have come up with, we have come up, should we say, with these 8 strategic goals. I mean, I don't want to go over all of them. We don't have the time. It's probably not even interesting for you. I would just want to focus your attention on one of these, which is this stakeholders objective, which is to forge relationship with other infrastructure providers, research infrastructure, and other stakeholders for the benefit of the RNE community. If we look at the text, which again, I will not read, that's not the point, I just want to highlight your attention on one aspect, which we call the integrated delivery of services. So this means that this the more concrete aspect of the strategic goal, which is about creating new added value services together with other stakeholders, other RNE infrastructure in a way that is compatible to preserve the nature of GEANT and the NREN. Now, I've kind of explained, the who, what, and how. Let's just focus ourselves on the why. So why we do this? So I will just start with the question to the audience. How many people have ever used one thing like this? Okay. Only 3, which is good, just 3. So maybe more people have used something like this, I can imagine. Well, this was pretty much the entry point to the internet service for, Generation X and later on. So this was what it was about to connect to the internet. So you have to, dial up, put the number of someone that was kind enough, probably stealing from your father's office or something like that, go through the whole shenanigan and then wait online. And then at some point you had Mosaic opening up, or Netscape, depending on your age. And all this now this is what it looks like now. Now, you can use your voice. You don't even need to touch it. You can just keep it there on the mantelpiece. Now, while these two pictures looks incredibly different, the reality is that this is not a revolution from the previous picture. This is just an evolution. Yes, dramatic. Yeah, we agree on that. But everything that was in the picture before is in this one. So this is still a von Neumann infrastructure, of a machine, and you have an I/O device, CPU, RAM, a modem inside, everything all the same. Just smaller, more powerful, consumes less and everything. But it's just the same, more or less the same. But there was a dramatic revolution between these two pictures. This was the revolution. It's the users have changed. The users have dramatically changed. The people that used to use the internet a while ago, they had, very different skills. People today, they have other priorities in life than spending 20 minutes to connect to the internet. They want to do, other things. All our devices today are already connected. I mean, we don't even have to connect to the internet. We have to disconnect them if that's the case. They just, as soon as they boot up, they are already connected. And of course, the same is true for the RNE users community. Their priorities have changed dramatically. The way of using our infrastructure has changed dramatically. They used to be focused on the infrastructure and services about the infrastructure, but now their focus is on data. Now the focus is on, data sets, metadata. That's the currency of our user community right now. They don't care about infrastructure services anymore. Well, they do care, but they don't even realize, because it's all transparent for them. If we look at the network cost trend, you see that over the years the cost has gone down so much, and if we compare to other technologies, now, for example, if you look the cost of 1 terabyte of mechanical storage from 20 years ago, the decrease in price is dramatic. It's like 99-point-something%. But there are other things to take into account, which is not just the technological cost. If you look at the cost of producing the data, now, applying the same ratio that we found before about the storage, the cost of sequencing a genome will be in 2022 something like roughly $400,000, using the same decrease of the storage. The reality is that the cost was $400. So the decrease in cost is so much steeper and so much dramatic. Then you have something like this now. Things that pop up on your internet to advertise, sequencing your genome for $200. This, of course, shows the incredible gap between the cost of producing scientific data and storing scientific data. This gap is become one of the major problems of today's data production. If we look back again at the sequencing genomic data, some of the result of this dramatic distance between the cost of producing data and the cost of the storage has seen people coming up with creative solutions. Like, for example, in genomic data, a lot of people now don't do long-term preservation anymore for sequencing data. They just use the data, they analyze, and then they drop it away. And then, in case they need it at a later stage, they just start again sequencing from the original specimen. But of course, this is not always possible, especially when we deal with organic data, because the the sample would be depleted over time. You know, you cannot go on forever. You know, you have to stop at some point. Other approach, for example, from the LHC community is getting rid of derivative data. So you only keep raw data, you do the backup of the raw data, and the derivative data is reprocessed again in case there is the need. So they are not stored anymore long term. This normally is the answer to all these problems. Clouds. That's what people like to, you know, that's the solution to every problem. Well, it's not that simple. Procurement could be an issue, especially for a publicly funded organization. It's not always that easy to buy off-the-shelf cloud services. There are hidden costs a lot of times, you know, like, for example, retrieving your data when you finished using a cloud service. Sometimes they charge you to just take back your data, which is bonkers, but it's like, you know, a ransom in a way. Performance are sometimes not always as expected, especially for data processes that are very heavy on you know, CPU load or expected I/O performance, and also the integration with the existing scientific pipeline is not always straightforward. You know, sometimes, you know, you go through a very steep learning curve to just integrate these cloud resources into your existing infrastructure. But despite all of this, this is the trend. So there's no denying, and you know, it's pointless to resist. This is, for example, the annual consumption of the giant IaaS framework, which is a framework that the NREN community in Europe can use to buy cloud services at more convenient condition and price. And if you see the increase of the cost, of the consumption in millions of euros, is you know, it just shows the trend. And you know, 2024 is not even complete; it just stops at Q3. A different way of looking at this, if you look at the distribution of the ownership of cables around the world. In 2010, the vast majority, of course, there were telco, ISPs. Today, the majority of the cable system is owned by content provider and you know, social networks in some cases. But in the meantime, the big science that, you know, the NREN community serves doesn't stop. So big facilities are progressing or being built, you know, despite sometimes delays due to, you know, other geopolitical factor, from pandemics to worse. But in the next 2 decades, there will be a large score of new big science facilities that will come up online or will reach production level. Then that will be a huge deluge of data hitting our networks. If we just give a look at the relative size of the amount of data produced over time by the different projects, you can see that from you know, the first run and second run of LHC, the size of this data is going up and up and up. And we need to think about long term how we're going to deal with this amount. A few years ago, we did an analysis internally in Giant about the future needs of our intercontinental capacity. So we highlighted what was the trend from the known community of big data that big science that we knew, and we came up with this trend that you can see clearly that there is a definitely remarkable growth, and especially in some areas of the world. For example, you see that there is a big increase of the foreseen traffic to Asia, because, you know, there are a lot of facilities that are hosted in Asia, but also there are a lot of Asian countries that participate in very large experiments like ITER or SKA, and WCG, of course. If you look at the amount, we are looking at something in the region of 2 to 3 terabits of data between 2025 and 2026, which is basically today or tomorrow. But if you look at the total amount of data that is already moving on the Giant backward, which is close to 2 terabits, this is just a massive amount of data that needs to be moved around. So this is not something that can simply be achieved just with buying additional infrastructure and just, you know, throwing money at it. I mean, starting from the fact that, you know, we just don't have so much money. You know, flat budget is just an optimistic approach, an optimistic hope. We are not even on flat budget. We know we are on shrinking budget for science. We are seeing this from our perspective as the user group in Jeonghoon in terms of the kind of services and community we are serving now, because more and more we are now giving services not directly to end user, but to providers of other services. So we are becoming infrastructure providers for other infrastructure providers, which is a bit of a change of the scenario we were used to before. So to summarize, I think I've given you, food for thoughts about the different challenges that the NREN are facing. So one, as I've said, comes from the shift in the user model and the push from the market, of course. The other one comes, again, from science that keeps going, keeps growing, and wants to achieve bigger and bolder objectives. But, of course, there is always the geopolitical world that pushes on us, governments, funding agency, legislation that changes, and this clearly is one of the strongest influence factor for the NREN community, which tend to be quite aligned with the government in way or another. And the last one I want to mention, but not in terms of importance, is the challenge coming from the green policy and the net zero challenge, because this is something that cannot be really ignored by enterprises that have the aspiration to serve the society in a sustainable and ethical way, which is surely something that is part of the NREN mission. Thank you.
Thank you. Thank you, Capone. Yes, very interesting topics. We're still discussing and the collaboration, those technology on those areas, because the APRP working group is always based on this, the big data, and we want to deploy the big data superhighway based on distributed HPC. And currently we focus on just the scientific data, and in the near future we should interesting as you mentioned, all kind of contents. Yes, thank you and give claps again. And the next speaker is Ghulam Mustafa. He came from the Sakra IBA University in Pakistan as a remote. And he can say the AI science in Pakistan and the related work and why need the distributed HPC the environment. GM, are you there? Okay. Whenever you're ready,
yes,
start.
well, thank you. Thank you so much. May I start?
Yes, start.
Okay, thank you so much for the opportunity. This is Professor Dr. Ghulam Mustafa Sheikh from Sakkar IB University, Pakistan. So I will present a brief about the Sakkar IB University and the facilities which are available at Sakkar IB University to perform the AI activities and to run the AI activities. So I'll briefly talk about the computational resources which we are using for running the AI tasks, and of course some of the challenges and future requirements for the computational resources in terms of HPC. So to start with, this is basically the beautiful campus of Sakkar IB University. So it's a public sector university in Pakistan, located in the rural areas of Pakistan. And it's a degree awarding university. So we have 4 different faculties at Sakkar IB University. We have Faculty of Science and IT, we have Faculty of Management Sciences, Faculty of Engineering, and Faculty of Education. I basically belongs to Faculty of Science and IT. So Faculty of Science and IT has 2 different departments. One is Department of Computer Science and Department of Mathematics. So I belong to the Department of Computer Science. So at the Department of Computer Science, we offer several degree programs, starting with the BSCS with a specialization in AI. We also offer software engineering, master programs such as MSCS, MSAI, software engineering, and we also offer a doctorate program in computer science. So at the Department of Computer Science, we have several labs. If I specifically talk about the AI and robotics, so we have a lab called CRAB Lab. So its full name is Center of Excellence for Robotics, AI, and Blockchain. So we call it a CRAB Lab. We also have some other labs like software engineering labs, data science lab, 3D animation and gaming lab, and fabrication lab, which is from the MIT, USA. So this is the CRAB Lab introduction. So we have 3 different clusters at CRAB Lab, starting with the robotics cluster, AI cluster, and blockchain cluster. So every cluster has a different teams working on in that lab. So this is the outlook of the CRAB Lab. So we have different machines available, different platforms available. So these are some of the platforms which are available at CRAB Lab related to the robotics. These are the machines which we use at CRAB Lab, having GPU-based machines. So this is the the computational power of the GPU-based machines which are available at CRAB Lab. So we have machines having dual GPU of NVIDIA 2080. We have multi-core processors available. Each PC has 64 RAM. So we actually dedicate these PCs for MS and PhD students. They perform the AI-related experiments. And all the machines contain Linux and Windows operating systems. So these are some of the activities which we perform at CRAB Lab. So briefly, I will talk about some of the projects which we have done at CRAB Lab. So this is one of the project called CallSense. So it's basically the SaaS-based tool which is available at callsense.ai URL. So the aim of this project is to elicit the emotions and aspects from the audio calls. So actually, this was a collaborative project between the Cybrid, which is the Lexan Group company of Pakistan, and IBA and HEC. So the funding was provided by the HEC under the National Research Project for Universities, or NRPU scheme. So basically, this project does what is actually it takes all the audio calls and it can elicit the emotions and aspects from the audio calls. So this is available on callsense.ai, and we offer the services as SaaS-based. So we have deployed this on Amazon Cloud to provide the services. So this is brief methodology of this project. Actually, is mentioned earlier. It will accept the audio calls and elicit the emotions from the audio calls. So whether the calls are in English or Urdu or in any language. So through the help of large language models, we have processed those audio calls and to discover the emotions and aspects from those audio calls. So we provide this service to different call centers. So our call centers use this tool to elicit the emotions and aspects from the audio calls. So these are some of the results from the audio calls. For example, the screen shows 3 different audio calls, and it elicits the sentiment and different aspects from the audio calls. So we have published actually 2 papers on this tool also. So one is the systematic literature review and the other one is the experimental paper, which are available online. So this is another project where we were interested to detect the fake reviews from the derived.pk. So, everybody is interested to buy or sell products online. So most of the users put fake reviews on derived.pk, and mostly the users write the comments in English or Roman Urdu. So our algorithm actually detect the fake reviews based on the user behavioral features. So we have experimented different features such as textual features, lingual features, and behavioral features. So we found behavioral features are most important to predict the fake reviews from online platforms. So we performed several algorithms related to machine learning and deep learning. So we found like gradient boosting algorithms, extreme gradient boosting algorithm perform the best compared to the deep learning and other machine learning algorithms. So we have submitted this paper in ACM transactions. So we have recently received the minor revisions a few days back. So hopefully it will be published here in SCM Transactions. So another project is the fine-grained multilingual hate-speech detection. So we perform actually the hate-speech detection using, again, transformer-based approaches. So we employed latest algorithms such as Robota, BERT, and we also employed the explainable AI to interpret the model outcome. So this is simple methodology where we collected the data written in English. We translate the data in also Urdu and Sindhi to detect the hate speech in other languages also. So you can see here we employed the transformer-based approaches here to detect the hate speech from social media. We also employed the explainable AI LIME algorithm to explain the outcome. So we can see here XLM Robota outperform. And so we perform the binary class classification and also the multi-class classification. So in binary class, we just perform whether the review is actually belonging to the hate speech or not. If yes, then what type of hate speech is there, whether it is talking about the disability or gender discrimination, nationality, ethnicity, or religion. So these are some of the outcomes of the explainable AI where, I mean, our model does not just predict whether the tweet is hate speech or not, but it's also explaining why our classifier, classify it into either hate speech or non-hate speech. So you can see we have employed different languages, like it can detect hate speech from English as well as Urdu. Okay. So this is another project. So this is the last project I'll talk about. Then I'll move toward HPC. So this is to detect the post-flood scenario using the semantic segmentation and classification approaches. So again, this is the funded project by Higher Education Commission, Sindh Higher Education Commission. So we were interested to detect the impact of flood using the aerial images. So we took the aerial images using the drone and we classify image whether there's a flood or not. If yes, then our algorithm can detect what is happening in the scene, like is the building flooded or not? Is the road flooded or not? Are there any trees or pools? So our algorithm can interpret the scene also. So regarding the computational requirements, so as mentioned in our lab, we just have the GPU-based machines. So, and we cannot perform the detailed AI or complex AI task using these machines. So these are not capable of performing those complex tasks. So to mitigate that, we have two options. Either we can go for collab or we have a strong collaboration with one of the university in Norway, which is NTNU. So our researchers most of the time visit there for an exchange program and in NORPOD Connect project and CBHE Erasmus Plus project. So they perform detailed or complex analysis using their cluster called EDUN. So if I talk about the EDU, so it's a high power distributed cluster having the total computing node 188, having total CPU cores 8580, and total GPUs are around 234. Storage size is 550 terabytes. So if I talk about the GPUs, the EDU has around 28 P100 GPUs and 40 V100 GPUs, and A100 GPUs are 106 and 56 H100 GPUs. So these are different nodes. Of these nodes, there are some of the computing nodes and there are some of the GPU nodes. So when we normally we perform the experiments using Colab or this EDU, and when it comes to the deployment, we often deploy our application on AWS or GCP, which is Google Cloud Platform, or Azure. So most of the time we use AWS. And recently in Pakistan, we have a company called Rapid Compute. They also provide very good resources to deploy the AI applications or simple web portals. So future requirements, of course, in our area, there's no dedicated HPC. So we are aiming to, push the government to fund us for establishing the HPC because in the area where we live has 5 different universities. So we are aiming to form a consortium to, to write the proposal to the government. So we have already submitted it. So it's under consideration. So hopefully we will get that funding so that we can establish the HPC for all the local universities in our area. So this is it. So thank you from my side. If any question you have.
Thank you, the Professor GM. And the Pakistan IBM University is one of the core members of the APRP working group. And several years ago, we together to process the TAME project. And the IBM University in charge of the third party, such like AI science. Thank you again, GM. And
Thank you.
the
Thank you.
next speaker I will introduce is Seungmin Kim. He is the medical student, medical university student. He came from Yonsei University Medical of Medicine, and he will talking about his the actual experience how to using the NRP and what his topic. The NRP is a national research platform. Is the highest and advanced research platforms in the world. And Seungmin Kim, are you there?
Yes, can you hear me?
Yes, whenever you're ready, and go start.
All right, hello everyone. Thank you for joining, and I also thank Dr. Moon for inviting me. Okay, let me first introduce our team and myself. Well, I am a medical student at Yonsei University College of Medicine in South Korea, and I have also briefly worked as a junior specialist at the San Diego Supercomputing Center. So I have had the privilege to work with several wonderful people, including the pioneers of computer graphics and the internet, as well as grid computing. The National Research Platform was originally a Science DMZ data freeway, but however, it has evolved into a distributed cloud supercomputer. So Nautilus is the overlay which powers the National Research Platform, and it is a geo-distributed and federated Kubernetes cluster, and institutions contribute hardware within their own premises and join them through Science DMZ. So one notable aspect is that the current count of GPUs has been expanded by over 4 times the initial NSF award, which has been awarded to Dr. Frank Worswein. So this was the result of rapid community involvement and contribution of hardware in addition to usage. So I'd like to tell you why we have created Nautilus. So Kubernetes automatically distributes many containers to many nodes under a unified API, and containers isolate each workload into different Linux user space operating systems. So any Docker container runs on Kubernetes, and you could deploy your own containerized service like Amazon Web Services or Google Cloud Platforms. So this provides maximum flexibility. And it lies within the range of traditional high performance computing and virtual machines. So Nautilus is a DevOps platform in addition to job scheduling. So there are various productivity tools and research utilities which are hosted by the National Research Platform team for all users to utilize. And we also have diverse hardware, including GPU, distributed storage, FPGAs, and DPUs. Moreover, it's possible to expose your internal services using HTTPS, using HA proxy ingress. So I would like to point out that the number of GPUs have increased 4 times since the initial National Science Foundation grant. Moreover, there's nearly 20 petabytes of Ceph geo-distributed storage across the cluster. So this is an interface which outlines the resources available to Nautilus users. So with Nautilus, you are able to focus on your research, not the infrastructure. So When you contribute the node to the National Research Platform, there is an automated deployment and management procedure for your nodes which are inside your premises. So this dramatically reduces maintenance load due to standardized setup and centralized maintenance. And the resources for computing are abstracted, like how you use public clouds. So the goal of the National Research Platform's Nautilus hypercluster is to give you the cloud experience within your on-premise computing resources. So you could focus on your research instead of the hardware and operating system. So these are some examples of research productivity tools within Nautilus. There is an alternative to Office 365 or Google Workspaces, as well as a dedicated Jupyter Hub where it only takes a button click to deploy a GPU Jupyter instance. There are also various services which are provided by the team without any additional setup or subscriptions. So, so this is Light LLM, and this provides an API key which provides self-hosted models, which are managed by the NRP team, and includes many state-of-the-art open source and open weight models, which you have no restrictions in or any pricing structures that are required to be used in many commercial services. And there is also a ChatGPT-like interface as well. The next topic I would like to discuss is the rise of three-dimensional graphics for cloud and HPC. So there are massive emerging three-dimensional demand for Linux in HPC, including AI-based drug discovery and structural biology. Moreover, there are various interactive and urgent high-performance computing workloads which can be utilized within HPC infrastructure. Moreover, recent AI trends indicate that AI has transcended the traditional paradigm of regression and classification into text processing with ChatGPT and other transformer models, and then they has led to processing of visual and spatial data in an interactive way. One use case is regards our group in Yonsei University, led by Professor Jeongbum Henry Kim. The Yonsei Genome Editing Laboratory uses large-scale, high-throughput deep learning-based design of CRISPR gene editors, and we have published in various high-impact journals. By predicting the efficiency and activity of gene editors without lab experimentation, we are able to produce unforeseen scalability with time and cost savings. And our current interest regards structural design of gene editors and utilizing large language models to analyze gene editors. So one other example is AI-based protein generation. You are able to select a target, and then you are able to design a protein that binds or otherwise interacts with that site. So, moreover, more and more scientific workflows now require graphical interaction based on the example I've outlined before. But GPU-accelerated graphical Kubernetes containers were unexplored, and it required host access and Linux X11 display sockets exposed into the container from the host. So as an alternative, me and Dan Isla have developed Cellkeys. And Cellkeys was first an internal Google Cloud project created by Dan Isla, and it subsequently evolved to provide fully isolated GUI desktop containers for high-performance computing and Kubernetes workflows, and is now widely utilized in emerging public AI cloud services, including FastAI, RunPod, and TensorTalk. So it's possible to use high-performance computing like your own PC in front of you. So this is an example example video that a collaborator has taken, and I highly recommend taking a look of this video from the PDF file I have distributed. So in addition, Coder is a Visual Studio Code IDE in your web browser. So this is an example of the Selkies deployment. And if you see a bit below, you are able to access using Selkies Visual Studio Code Server, which is a web-based Visual Studio Code deployment, and also the desktop version of Visual Studio Code, as well as Secure Shell and Terminal. So I have included some extra resources and have uploaded the PDF file into the Sketch webpage in our session 1 webpage. So thank you very much, and thank you for joining.
Thank you, Seung-min Kim. Anybody question? I just expect just one.
It looks like you've got a really good platform there, particularly on the AI. Did you build your own hub software to support that, or was that something that was available open source?
All right. I couldn't hear the last part of the question.
Okay,
So could
sorry.
you say
Looks like you've been doing some really great work that we'd like to build on. For the machine learning component, I noticed you had the hub there. Was that something that you built yourself, or was there open source that you were able to utilize to make that hub functionality for the models?
Yeah, well, so like the container, the machine learning and deep learning containers that we have developed was initially created by Dmitry Mishin, who is an engineer in our team, and I have also contributed in testing real-life workloads, including PyTorch, TensorFlow, and JAX, and I currently participate in maintaining the AI workloads as well. And we have also incorporated various projects which are able to be self-hosted from GitHub or in various Docker containers, and we have deployed them in the Nautilus platform. So it is a combination of both hosted resources, self-hosted resources, which are open source projects, and open source projects that we have developed ourselves as well. So it is a combination of the two.
Just sorry, one more quick question. Are you using any sort of vulnerability scanning, something like Harbor, to actually look at the LLMs and the containers that you're deploying?
So we don't actively use a container scanning platform right now, but we are utilizing Falco, which is an active scanning mechanism and platform which scans various processes within a running container instead of a static container that hasn't been deployed. So while we would like to integrate static container scanning in the future, we are currently using process monitoring within the containers to monitor, for example, crypto miners and other malicious softwares, or other vulnerabilities.
Okay, thank you, Seung-min Kim, and it's really fantastic as a content. Thank you. And the next speaker is me, and I would finish within 5 minutes, please. 5 minutes. And the Seung-min Kim's presentation's content is the up-to-date, the highest level in the world. The NRP is a national research platform, and the APRP is Asia Pacific Research Platform, and the GRP is a global research platform. And APRP is its final goal is to become the part of this global scale. So in case of US NRP, and really remarkable the infrastructure for sharing their the super facilities and the computer resources and the third-party researchers, they don't care on the technology, how to integration, how to build up. They just using. It seems like it's PC in front of them. So I wanted to say this Asia Pacific Research Platform activities and the related work for especially CJK project and the KRP. CJK meaning is China, Japan, Korea. And I really briefly introduce the several topics. My name is Jeonghoon. I'm in charge of this APRP working group in APAN, and I came from KISTI in Korea. I belong to this KOREANET, the Korea Research Education Networking Department, and over 20 years. And recently, the global trend in the research field, in the IT field, is the large-scale integration of the national IT resources for open source, open science. In particular, the U.S. has put a lot of the effort into the achieving the open science, and the actual results are being produced. The borderless research is being conducted through the field of the artificial intelligence, represented by the LLM, and unrestricted research is being conducted through the open source. So therefore, in order to achieve the practical and the specific, the open science, we are putting a lot of the effort into the properly creating open science equal the open infrastructure plus open data plus open source. The open source meaning is include the open compute, the open storage, and the open the CDN and the open device and the open IoT and blah blah blah. In the near future, we should include several new technologies. And on top of this infrastructure achievement, we are covering not only the scientific field but also the social science, the humanities, and the fields through the AI plus open science. In my opinion, the two representative approaches and infrastructures for these are the one is NRP, leading by the UCSD and the San Diego Supercomputing Center by NSF. And the second thing is IRI, the integrated resource infrastructure, leading by ESNet, centered on the DOE, the organizations. Based on this global trend, the CJK, the collaborated project in the Northeast Asia, the APAN, APRP activities, the Korea Research Forum, and the various approaches are being carried out in various countries and the communities. So I will introduce the CJK collaborated project and the various activities in the rest of my presentations. This is the first one is a CJK, the collaborated project in Northeast Asia. Second thing is APAN APRP group. The third thing is a Korea Research Platform, the current status and related work. And finally, the ASEAN, the Korea HPC project, overview of how to deploy, how to build ASEAN countries as HPC. And I want to just skip, and this is a CJK team, China, Japan, Korea. And the final aim is how to share HPC infrastructure and how to transmit the big data, how to using all those infrastructure combination big data for open science, each countries. Our strategies is the Korea, Japan, and our strategies is divided in 4 units. Unit 1 is the infrastructure, second is data transfer, third is data compressor, fourth metadata unit. I want to skip and more detail. And this is a Korean status. The Korean KRP is aimed to the HPC over HPN. HPN meaning is a high performance network and a high bandwidth distributed HPC in Korea domestic areas. And from now is the APAN, the APRP working group. It's since 2018, and we through the several the working group, the meetings, and so far we gathered these two collaborated international project, Asia Connect project, and the CJK collaborated project in Northeast Asia. And the last APAN meetings is summary, and I want to skip. And we have the prototype, this APRP research platform, the actual cluster system at the build at UPM University in Malaysia. And the third thing is a Korea research platform, KRP. The KRP, the Korea have 25 national government-funded national research institute. We want to deploy this research platform, establish the high reliability and the high-speed transfer system without boundaries between participants. The speakers before, as they mentioned about is the data transfer, the barrier, and the using the HPC barrier. So the Korea KRP aim to the get rid of the barrier without boundaries, each institute. So from 2015, the KRP is became the global partner of PRP and the NRP project so far, and since 2024, CJK collaboration project. And we have the several related projects, and the final one is medical areas. And the last one is the ASEAN, the Korea HPC project. The ASEAN countries consists of 10 countries, Laos, Cambodia, and such like countries. They want to build this HPC, and KISTI in Korea and ASEAN collaborated with them and deploy and set up the HPC until this year. And how to how to managing all the topics include this project. And briefly, the system, this requirement and the specification is such like that: 3.5 petaflops and 3 petabyte storage and 400 giga BPS in the international or domestic networking specifications. And this is a layout of the HPC. Okay, and I quick through this my presentation file, and the conclusion is I want to expand the infrastructure to the ASEAN regions, because many peoples and the following this the components is slide. The ASEAN is the data the race is so rapidly as in the near future, and the ASEAN areas is the many we have many the smart the brain, the AI, bio, and the third-party researchers, but we don't have enough the HPC infrastructure or the computer resource. And the APRP and NRP or GRP can and support distributed HPC environment to what they need. And the second thing is activated of the APRP. All those topics is I want to deploy this through APRP working group, and then we want to discover is new third-party parties, research areas, and to deploy and this infrastructure and our communities. Thank you for your listening, and I wanted to make up this session 1. Sorry.
Can I ask a question?
Yeah.
Before you make up, the brim, is it up already, or when is it going to be up?
What pardon?
ASEAN HPC,
Yeah.
is it up?
Yes.
It's working?
Yeah, not working. And they have, until this year, set up the prototype system at Indonesia.
Okay.
Yes.
How can we get involved with that, and who's the person
Yes.
to
All these facilities belong to this ASEAN countries. You know that is 10 countries consist of the ASEAN countries,
Yeah.
and their headquarters and HPC task force teams and discussion, how to using, how to share infrastructure.
Thank you, Jeonghoon, and thank you, everyone. I'm Andrew Howard from National Computational Infrastructure in Australia. Our agenda today, I'll be talking about what NCI is, just giving you a brief overview, and then providing some NCI updates. First of all, I'd like to welcome our new interim director, Dr. Sean Smith. The former director left the ANU and NCI in December 2024. Professor Andrew Roll will commence as interim NCI director on the 24th of March. Andrew brings extensive HPC experience, extensive organisational change management experience, and is actually a field expert in AI and HPC. I'd like to introduce what NCI is. We're the National Computational Infrastructure. We're Australia's high-performance computing service. We provide comprehensive vertically integrated research services, national access on priority and merit, driven by research objectives. We operate under a formal collaboration between the Australian National University, the Commonwealth Scientific and Industrial Research Organisation, CSIRO, the Australian Bureau of Meteorology, and the Geoscience Australia, our government agency which deals with minerals, geoscience, etc. We're also a partnership with research-intensive universities, which are supported by the Australian Research Council. NCI is directly funded by the Australian Government through the Department of Education, Skills and Employment National Collaborative Research Infrastructure Strategy, NCRES. We were most honoured last week to attend the NCRES Forum and present our plans for procurement moving forward on a new system. We're located in Canberra, Australia, which is on the east coast, halfway between Sydney and Melbourne, up in the mountains. Canberra is our national capital. Our sister computing centre, Pawsey, is on the west coast of Australia. So collectively, we cover the whole range of science, and we tend to distribute the workloads based on the specialty or requirements. Our systems are designed slightly differently. We're more CPU-oriented currently, and they're more GPU-oriented. We cover the complete range of science from fundamental, strategic, applied and industrial sciences. We cover pretty much everything except radio astronomy. Our sister centre, Pawsey, does the majority of the radio astronomy work with the building of the Square Kilometre Array at the top part of Western Australia. Our primary system is called Gardi, which comes from the local Ngunnawal language. The Ngunnawal people are the traditional owners of the Canberra area. We commissioned that in January 2020, so the machine is starting to reach old age. We are intending to go to market for a new machine at around $100 million budget. That is still to be confirmed by our national government, but we're expecting an announcement before the next federal election is called, which we anticipate will happen in the next 2 to 3 weeks. So currently we've got Cascade Lake nodes. We did a mid-cycle upgrade to include Sapphire Rapids nodes as well. We've got large memory nodes, large compute bandwidth, so some very old Broadwell Xeon cores, which we're using typically as our login and front-end user services, delivered via what we call ARE, or Australian Research Environments. That's a graphical front end to our high-performance computing based on Ohio State University's open on-demand product. We found that is a extremely well-developed package and delights our users. They can use a web-based access to access all NCI capabilities. They don't need to install any tools on their machines, which for those coming from university-managed IT departments who are very prescriptive about what applications get installed, means that they can just start working on NCI immediately without having to wait for local IT. However, all of this computation is only there to extract the value from the data. As we've heard from previous speakers, we've moved from the wires and all the interconnection data is the key, and that's the thing we're all looking at and getting the maximum value out of. My team looks after cloud systems and innovation. We have our NREN cloud. NREN comes from the Wiradjuri language, which is the First Nations people which borders the Ngunnawal group. Our NREN cloud is an OpenStack-based system, which we also use to support entry-level HPC workloads. We have Kubernetes capability as part of that. We are actually doing in-tenancy Kubernetes rather than a whole-scale Kubernetes. We have Ansible playbooks which allow our users to quickly spin up their own Kubernetes environments and tear them down as needed. NREN is used by both NCI for delivery of our data services portals and our stakeholders to deliver long-running and web-based service applications that don't typically fit onto an HPC system. Our NCI NREN cloud was comprised of repurposing our former high-performance computing system, Rygen. I was given 22 racks of Rygen nodes. This happened just as the pandemic was starting, when the university campus was closed. Only the managers were allowed on campus. So I had a fun time wiring up a 22 rack system. We switched it from InfiniBand to Ethernet, and that served us very well, but it's reaching its end of life. We've extended our government investment on old hardware by about 7 to 8 years. So it's a great benefit of reducing taxpayers' money, but still delivering a high science outcome. NREN supports our service delivery, so all of our public-facing services, data collections, data analytics and dashboards, data inflow and processing, service portals, and virtual laboratories and research environments, which are discipline-specific, containing the set of tools that a researcher would need to easily get started without having to go through all the monotonous work as a computer scientist would do. We also support NCI stakeholders. NREN is a delivery platform of many of our stakeholders' cloud-based services. That includes our state government and federal government organisations. And we provide infrastructure as a service, which allows our stakeholders to configure and build what they need as they need it. I'm excited to announce that we are currently undergoing a hardware refresh of NREN. We've extended the life of the old HPC system extensively. The hardware is starting to fail and does not meet our users' performance requirements any longer. We have been allocated a 1.2 million Australian dollar budget to replace the majority of the hardware. Our approach to market has been completed and a vendor selected. The delivery date is to be decided, but the memo to the Chief Financial Officer at ANU was prepared and sent during the first session this morning. One of the most interesting things that we do is the Australian Copernicus Hub. As for those of you who were in the Disaster Management Working Group on Monday, Copernicus is a European space program. Rather than me talk about it, I'll play a quick video which describes how Copernicus works.
25 years ago, Copernicus set out on a mission to transform the way we see our planet. And as of today, it has established itself as the largest environmental monitoring program in the world, delivering a whopping 16 terabytes of high-quality data every single day. At the heart of the program are a family of satellites known as the Sentinels. The data collected address some of today's key challenges, like diminishing polar ice, food security, urbanization, natural disasters, and of course, climate change. Copernicus also supports tens of thousands of jobs and generates billions of euros in economic benefits. While the European Union is at the core of the program, ESA develops, builds, and launches the satellites on their behalf. These missions carry a range of technologies for land, ocean, and atmospheric monitoring. Sentinel-1, the first of the series, is an all-weather day and night radar mission covering the land and ocean. Its data is used to map floods, witness glaciers in motion, icebergs snapping off, survey oil spills, and detect ships for maritime security. It's also used for monitoring ground deformation from subsidence, earthquakes, and volcanoes. Sentinel-2 provides high-resolution optical imagery for land monitoring. It's been used to monitor agriculture and crops, coastal erosion, algal blooms, deforestation, urbanization, and even penguin colonies from space. Sentinel-3 measures Earth's oceans, land, ice, and atmosphere. It measures sea surface temperature and sea surface height to track the evolution of El Niño events. With its ability to measure ground surface temperature, it can help monitor the outbreak of wildfires and heat waves. With its wide view, it can image contrails, cyclones and hurricanes, oceans, and even entire countries. Sentinel-4 and 5, yet to be launched, will provide data for atmospheric monitoring, while Sentinel-5P maps a range of trace gases affecting the air we breathe. Over the years, it has mapped global methane emissions and even nitrogen dioxide during COVID lockdowns. It's monitored the ozone hole, tracked aerosols from fires, sulfur dioxide from volcanoes, as well as desert dust. Lastly, Sentinel-6 carries a radar altimeter to measure changes in global sea level, mapping 95% of Earth's ice-free ocean every 10 days. Individually, the Sentinels provide strategic data, but their true strength is unlocked when their observations are merged and combined, even complementing other ESA satellites for a better understanding of Earth's dynamics. The data are also fed into long-term data sets to study climate change trends and impacts over time. Building on the success of the Sentinels, 6 new expansion missions were selected to join the current fleet, expanding their current capabilities to address the EU Green Deal and gaps in Copernicus user needs. One of which is the Copernicus Anthropogenic Carbon Dioxide Monitoring Mission, the first to measure atmospheric carbon dioxide produced by human activity. Today, Copernicus is the largest space data provider in the world. It has now accrued over 700,000 users who have downloaded more than 540 petabytes of data. But this is just the beginning. ESA is now expanding its data distribution through the Copernicus Data Space ecosystem, offering easy and instant access to Earth observation data from the Sentinels and other contributing missions, all of which is available free of charge to anyone in the world. With Earth observation entering a new era, Copernicus will keep providing the data you need to make informed decisions in our ever-changing world.
So our current area of interest that we cover ranges from the border between Afghanistan and Pakistan, across the southern part of China, and out into the Pacific. That's around 38% of global coverage. So this year we're pleased to announce that we've increased the coverage range to include all of continental Antarctica. As you heard, the new Copernicus Data Space ecosystem was implemented last year. The Australian Copernicus Hub is operated by my team at NCI on behalf of the Australian Government Geoscience Australia. The current hub's been in operation for around 12 years, and it is supported using software developed by myself and my team around 12 years ago. So we're keen to retire some technical debt that we've got in there. We've got over 12 years of accumulated Earth observation data, which is currently around 5 petabytes. The cost of operation for Geoscience Australia is around $1 million per annum. This delivers a $5 billion per annum GDP input, with the GDP input projected to grow by 2030 to 30 billion Australian dollars. The new European standards were introduced in 2003 with planned introduction, 2023 with planned introduction in 2024. And I'm pleased to announce that Australia is the first nation to deliver web-based services using the new CDSE. Our current production status in recent weeks, in collaboration with our French development partner Gale Space Systems, we've increased the download speed by around 10 times and are currently delivering 16 terabytes of data from Europe to Australia every day. We did a beta release to our state government agencies on the 1st of February, and we'll be moving into full production on the 1st of March. Our final production release and tuning is anticipated on the 1st of April. The old data will continue to be available in read-only mode on our current system, and we'll be progressively integrating that data into the new system over 2025. And as I mentioned, we're expanding our region of interest to include the complete Antarctic coverage. There are other hubs in Asia. Our Philippines colleagues are currently in installation of their Copernicus hub. And I'd like to mention our Australian Digital Earth product. But also I should mention that all of the Gale software that's been developed has been open sourced by the Australian government and is freely available for you to use. We also have a number of Digital Earth programs, which are digital twins. Antarctica is currently being built. We have an existing Australian hub, an African hub, and a Pacific Digital Earth. I'd like to quickly announce or pre-announce Australian Intelligence, which is our artificial intelligence capability. We'll be announcing that next week at Supercomputing Asia. And that will be integrated into our Australian research environments, providing our users with a single point-and-click interface to utilise artificial intelligence and new machine learning models for data analysis. So, in conclusion, all of the Sentinel data is freely available, and I'd like to thank the European Space Agency and our partners Jeonghoon for providing the transport systems. Our state government agencies have switched to using the new hub, and full public release will happen on the 1st of March. If you need access to this data, the Australian Copernicus hub may provide you faster access than the European hub, and we welcome you to use it. So running 4 minutes over time, any questions? If not, maybe catch me at the...
Any question?
Hi, Andrew. Thanks for the very interesting talk. I'm just wondering, you just now you said you inherited an old supercomputer,
Yeah.
and you tore away the infinity band and replaced it by Ethernet.
Yeah.
100 gig and 50 odd gig.
56, yeah.
56 gig. Do you see any what were some of the major challenges that you have running that?
It was actually pretty easy. We used the ConnectX-3 cards, which are operable in either InfiniBand or Ethernet mode. So we just purchased some 100 gig Ethernet switches and run them at 100 or 56 gig.
Oh, okay.
So
it was quite easy and much lower cost.
Yeah.
Much lower cost. How are you coordinating your Copernicus hub with the Philippines new hub that's going to be set up in the Philippines?
I'm consulting with them. We're providing free consultation and guidance on best practice for network tuning to actually achieve that 16 terabytes per day.
Okay, so you're downloading your data from the Europe, right?
Yes.
So you're coming through
Singapore
and coming through the NRENs.
Yes.
Okay, that's important.
Yeah.
Okay.
Okay, next week we meet again, talking about that again. Thank you for Andrew. And I want to introduce as the next speaker as Kiwook Kim. He came from KISTI in Korea. And today's topic is the high bandwidth distributed HPC for the agricultural areas.
Hello everyone. My name is Kiwook Kim. I work at KISTI from Korea. KISTI is developing a big data management platform based on a container environment called KRP. KRP is Korea Research Platform. We applied the big data management platform to the agricultural research field and conducted an agricultural big data research platform development project. Today, I will explain this project in detail. I will explain in the following order. First, research background. We want to construct a big data ecosystem using a system that can utilize data collected by the Rural Development Administration. In the existing agricultural sector, efforts have been made to collect and build data and models. Therefore, we aim to create an environment where agricultural models and data can be easily accessed by researchers and shared and utilized by each other. Traditionally, researchers in agriculture have kept their data and models separately. We want to create an environment where they can collect them on one platform and share them with each other. In addition, most agriculture models use old programming language. Most of the existing language are Fortran. Yeah, so we will convert them to the latest programming language and create an environment for development. We build a container-based agriculture big data platform using Kubernetes container automation technology. And we unify models composed of various languages. And we configure those models in the form of APIs to operate in a container environment. And we provide a web interface environment to improve user accessibility. Next, we will explain the overview of the project. The project name is Development of an Integrated System for Application of Agricultural Big Data and Models. The project started in April 2022 and run for 3 years. The total amount is approximately $677,000. The main organization is Seoul National University, and KISTI is participating as a joint research organization. The goal of this project is to develop a platform that provides API services for third-party developers to deliver information to end user based on agriculture models and data containers. This system uses the model API, which is developed to convert each agricultural crop model into an API so that machine learning performance results can be obtained simply by executing the APIs. This project was carried out by 3 organizations. The Rural Development Administration provides major agricultural big data and models and build a system to manage them. Seoul National University builds agricultural models in the form of APIs and provides them to users through a web interface. And KISTI builds a backend system for a platform to provide container-based agriculture model APIs and provides a web interface for administrators to use them. I will show you the current status of system development. Let me explain the overall configuration of the system with an explain in the white box. The example in the white box is a machine learning example that predicts the amount of water according to irrigation conditions. In fact, if you look at the example in the white box, you can perform the following steps based on the result using various data and models. First, you can perform the crop growth simulation experiment using soil and water data and the result using the model, and measure the predict irrigation amount using the performed values. Containers that have converted these various models into APIs are saved as images, and the saved images are saved for backup purpose because problems may occur. Images saved for backup purpose are created as containers in Kubernetes and provide model API services. Then, the data to be used for each model is stored in storage. And the object storage required by each model API is called and used. These data are called from the data storage provided by a rural development administrator and stored in the system's object storage. Using the image developed at Seoul National University, the backend system uses development container images service and ingress to configure an environment that can provide external services. And when accessing from the outside, the system can be used by connecting to the following website through domain connecting using Nginx. The part currently being shown is the interface part developed by KISTI. As shown in the figure, we developed the membership, registration, and login part to distinguish users. And we configured an interface that only administrators can access to manage the Kubernetes, SAP, and monitoring system of the backend system. We developed it for the convenience of an administrator. And the user can easily change their password. We also created a page called My Token. This page was developed to authenticate user using the Model API. Model API users are required to use this token value to authenticate themselves when using the Model API. The token value is configured to generate a Python-based random string, and in order to receive this token value, it must be generated after signing up and receiving approval from the administrator. Seoul National University developed an environment that automatically performs machine learning by linking models and data as an API. And it provides a web interface as shown in this figure. The figure on the left shows an interface developed using open source Swagger. But the interface was redeveloped with that user can be in more easily in the future. And for security purpose, an API key was used. Then, select the data and receive the job ID value. The job ID value is used to distinguish users when multiple users run this model. And the result value is delivered. After that, if you select various parameters for the data and run machine learning, you can receive the result value. The API key is used by copying the value from the my token of the user system on the previous page. These are model APIs for agriculture and the environment developed by Seoul National University. All of the above models are provided with a web interface. Currently, a total of 26 models are provided. This project was completed last year. In the first year, we completed the infrastructure configuration and development using open source to develop the backend system. In the second year, we configured a login system for user management and performed work to link model APIs developed by Seoul National University and developed an interface for user and administrator. In the third year, we are conducting testing based on actual users and are working on transferring the platform to the rural development administration systems. Thank you for listening my presentation.
Thank you, Kim. Yes, anybody question about that? I have one comment is I just to find out is we should be the well meet the application areas and the service provider areas. The third party researchers they have a big barrier to get into this the system layer, the how to build, how to using, how to managing. But in case of a research platform is we can provide as the system layer as the virtually. So in case of the deploy for agriculture areas, very big examples is the how to go to the next stage APRP working group. Thank you so much, Mr. Kim.
Thank you.
Yes. The next speaker is the Nur Asila Wati Abdul Hamid. She as the remoter and she came from this UPM in Malaysia, and she talking about is new project establishment is HPC in UPM. Asila, are you there?
Yeah. Hi, Jeonghoon. How are you?
Okay, I'm fine. Whenever you're ready, and start.
Okay. Can everyone see my slide?
Yes, that's good.
Okay. Thank you. Okay. Hello, everyone. Thank you, Jeonghoon, for introduction. My name is Nur Azila. I am from Universiti Putra, Malaysia. So today I would like to share about the our HPC, high performance computing in UPM, and also what we are doing with the HPC in our university. Okay. So recently, HPC has been very demanding in UPM. I can say that maybe since 5 years ago. So the demands are from several research fields such as the bioinformatics, AI, computational chemistry, engineering, and many more. And this is some resources that we had in UPM, from very small high-performance desktop to intermediate size of HPC. And this is the first HPC that we had. Maybe it's not really the first. We had previous ago, maybe in 2000, but very old. But this one already obsolete, but due to this HPC, we managed to get the new budget from Malaysian budget to buy for the new HPC. So thanks for this machine. And this is the second one, or the first HPC that we had. We had the GPU, Volta V100, although it's quite small, but it is very useful for our postgrad and undergraduate. We managed to keep up with the latest technology with this just a small HPC. And recently, as what Dr. Jeonghoon mentioned just now, we get involved in this project with the Korea, Australia, and Pakistan. So with this project, we managed to get the resources. So thank you for this project. Because of this, our researcher managed to reduce their processing time. As you can see, from 3 months to 9 days, and Python's Quantum Espresso from 3 days to 22 hours. And we looking forward for more reductions of execution time with our expecting new HPC, but I guess maybe by end of this year. So we set up our website and manage all the users with the resources provided from this project. And the current effort or options for HPC in UPMs, we managed to get the 12 Malaysian plan budget, and we also, some of us using the cloud services and PA data analysis company, collaborations with the Asia Connect project, and some of the HPC Advisory Council. This is some of our effort. And we also create awareness on the HPC since 2005 and several workshops and HPC conference until recent year. And we also invite some of renowned speakers, for example, Prof. D.K. Panda from US. And we have several projects from several research fields such as the agriculture, AI, engineering like the biomimetics, UAV collisions avoidance. All these are using our HPC. And recently, in order to to provide justifications and also to had more chances of the resources, we are doing some proof of concept between the on-premise HPC and AWS cloud. We are looking for the objective is, as you can see, looking at the technical feasibility, capacity, and so on. And this is still ongoing, and the method is we're going to choose several, maybe more. So we just started the kick-off a few days ago, and we had the free, it's not really free, the credits for 1 month to use the AWS. And although we had very decent HPC, but we managed to keep up with the latest technology and bring our students to the international conference, such as the HPC AI. And since 2020, we managed to get merit place in 2021, 2022, third place, 2023, merit place again, and recently, 2024, we managed to get the merit place and also award for excellence. So this is part of our effort to make sure that our students still are on the same path as the outside as the other country, and also was the same for our researcher. So we are glad that we managed to get the budget from our 12 Malaysian plans. So it's not that much, but it is a good amount, which is around USD 500,000. And we expected to have like maybe 1,000 core and also NVIDIA H200 for the GPU. So this the process of purchasing this and related to tender is still in progress. So hopefully maybe I can share on the next APAN. And we're also expecting the Asian shared HPC that mentioned by Jeonghoon this morning, which located at Brain, Indonesia. We also expected these resources to provide to our researcher. So I believe that's all from me on the progress or what we have done, basically in brief in our university related to the high performance computing. So thank you, everyone.
Thank you, Sheila. Anyway, the congratulations is new HPC project. Anybody question about that? In case of the UPM is one of the core members, and also the NCI from Australia is a core member of the APRP working group. Even though the Pakistan and the Malaysia is core PIs of the 10 Asia Connect project is the fifth core. And then Pakistan is AI science, is Malaysia is bioscience. And we can find out this through this presentation file, the several, the modeling and the simulations through the HPC is more and more important. So we can share and make the distributed environment using for the neighbors countries. Thank you, Pasila.
Thank you, Jeonghoon.
Yes, the next, I wanted to introduce the next speaker is Kaneyama Hidetomo-san. He came from the Riken Institute in Kobe, and he the expert engineers the Fukaku computer, and today he talking about is HPCI, the shared storage stream using the GFAM network file system. Yes.
Okay.
Okay.
So thank you very much, so Professor Moon. So and thank you for invite APAN and so APRP working group. So I'm Kaneyama from RCCS. So okay. So today is presentation about the HPC shared storage system and so GFAN file systems. So it is not so APRP working groups project. So this is national project. So but so this is this storage is stored HPC data, research data in Japan. So very important storage. Okay, and next slide. So sorry. So first is introduction myself. So my job is HPCI shared storage system and so flux operation. So I'm storage engineer. So HPCI shared storage is okay. So I'm sorry. Flux operation is so login node setup or client side data transfer setup or software install or so. But today focus is HPCI shared storage only. And so next is so this is a HPCI project introduction. So HPCI is high performance computer infrastructure. So it is so Japanese national project. So and so HPCI project provides so sharing HPCI environment and the supercomputer research resource and for researchers. So HPCI consists of many the national university and institutes. So for example, the Fugaku supercomputer in RCCS, and so SQUID in Osaka University, and so Tsubame is also Science Tokyo. So many university and supercomputer center including. So and the HPCI provides so essential service and infrastructure to use the HPC users and account management and so HPCI project selected or also help desk and so authentication IDP service. So HPCI have so many service provided, and so and network storage service have so HPCI. So this network storage service is HPCI shared storage service. So this is so HPCI shared storage introduction. So it is network storage for the sharing data between the supercomputer in Japan. So this project was started 2012, and so currently we are update and so install new systems. So currently, so the HPC shared storage is operated by the University of Tokyo and RCCS. So this system allows disaster recovery, so all shared research data. So we have the all data is 2 replicas. So the storage capacity, logical capacity is 50 petabyte, and so this so we have the 2 replicas. So physical capacity is 100 petabyte now. So we are currently in the process to introducing new 3rd generation systems now. So the logical capacity is expected that 90 petabyte or more. And so this is using this file system. So especially shared storage using the GFAM file system. So it is the base software and file system. And it is open source file systems, and so it is developed University Tsukuba and Professor Takebe. So this is the architecture and detailed architecture and 3rd phase architectures, and very simple design. So first is blue area, blue field. It is main architectures. So storage product is a DDN, so NVX2, and so we have the 10 set, and 90 petabyte or more. So storage type is hard disk, so we cannot buy the SSD. So because SSD is very high cost, so HPC shared storage system is a network file system, so IOPS isn't big deal. So we are I'm sorry. So we are priority. First priority is capacity. So we are choice the hard disk. So this storage could running the virtual machine, and so we set up the file server in the NVX2. So this storage controller could have the virtual machine. So storage controller have can install the virtual machines. So this storage so we have the 2 metadata servers, and so it is Dell product. So Dell 7XX product we buy, and so this have big memory and high speed SSD. So this area's machine will be connected, so the Arista switch, L2 switch, and every line is 100 gigabps bonding. And so Arista net switch uplink is 400 gigabps, and so total is 1 terabps. This is very rich setting, this rich configuring. And so Fugaku is internal connector is only 200 gigabps. So I think this is very lack now. So in future, I think update and this network bandwidth. So we must do the more speedy, high speed net access to the Fugaku and especially shared storage. So I'm sorry. So this is a skip now. So next is the SciNet. So this is a very important because we are we operated network file systems. SciNet is very important. So SciNet Japanese Scientific Information Network means provide NREN. So now SciNet is 6th generation, I think. So SciNet 6 is high-speed research network in Japan and connected to many universities and institutes. So because of HPCI and HPCI data center and HPCI shared storage using this network, so we really appreciate SciNet. So SciNet provides 400 gigabps full mesh network. So this is a very rich network bandwidth, very wide bandwidth, and so round trip time (RTT) is very fast. So Osaka to Tokyo is so about so 10 millisecond. I think very fast, and so covered around so 70 data center and so supported many network services. So this is the RCCS network. So we are connected to Signet data center, and so using the BGP. And Kobe DC line is 400 gigabps, and Osaka DC line is a dual 400 gigabps line from RCCS. So RCCS internal network is very rich, so 100 gigabit, 100 gigabps network, and so firewall, so using the FortiGate, so very rich. But very most important is the BGP service. So because so we are so we operate and so HPC shared storage is a network file systems. So for example, so base switch is failure or DC center is maintenance. So if cannot access one of the data center, so BGP will automatically so rerouting so and don't stop access. So this is very important. So we operate a network storage system. So network issue really to affect the HPC shared storage system service. So, but this setting is helpful to our service. So very important. Sorry, this is a skip. And so this is the GFAN file system introduction. So the GFAN file system is network file system. So of course, so parallel I/O can be used wide transfer bandwidth, and this basic so component, so metadata, so GFMD, metadata, and so file service, so GFSD, and client service, client API. So client API have a special command, so for the high-speed transfer, for example, so parallel I/O or so archive I/O or so split I/O. So the protocol is very simple, but today I have not time, so I'm sorry, this is skip. This is so protocol, I/O protocol. And so GFAM is very good function. So this is a so silent data corruption. So network and so storage sometimes broken file. So silent data corruption. So but so GFAM have so checksum, calculation checksum. So and sometimes using the checksum. So we can search we can search the so corruption data and so fixing. So and so this is program. So we have the one program in HPC shared storage. So as a network bandwidth, so this is programs. So the network bandwidth is high, very high, and so round trip time is very fast. So for example, so RCCS and University Tokyo is so 12 millisecond. So but HPCI data is many small file. HPC data is very small. So I think so kilobyte order or megabyte order, so very small. So if user transfer many small files, so when bottleneck becomes the bottlenecks, so TCP/IP or so GFAN protocol or client side access, so many bottleneck we have. So therefore we develop the GFPTA command. So this command concept is very simple. So client side archive, first is client side archive, and so parallel I/O, very simple. So it is very strong concept. So first, first is a listing directory, interdirectory, and so next is so archiving file per transfer, and so create file list, and so third is optional, but zip option, and so parallel I/O. So this is very strong. So many users are using this command now. So last is a future work. So this is so we present the Supercomputer Asia 25, the poster session. So in the next week, Singapore. So first is the collaboration to workflow tools for metadata annotation. So HPCI workflow tool is manage the supercomputer works. So HPC storage, for example, the raster and so BGF is not have the detailed metadata annotation. So only POSIX. So this is very lack and bad things. So because so many users cannot understand the old code data, so we now we need to the metadata, I think, but HPC storage have not metadata. So this concept is manage metadata in HPC environment without affixing service or systems. Nothing, only use the workflow. So we also consider storing information such as the names of the supercomputer, use the supercomputer's name or job ID or tags. So and annotation to the to use the save to the metadata in NoSQL. So next is So next is future work is next cloud access. So we focus integration with service. So while the GFAM API enable high-speed data transfer, so there are challenges in protocol integration with other service. So we cannot connect it to another service. So this is very problem. So we are thinking, and we also GFAM developed the next cloud module, and so next fiscal year, so we will using this module, and so connected another service, and so publish data service from the users, I think. So additionally, so future goal is enable the DOI assessment, and so publish research data in HPC shared storage. So access to the and this is the Gakuni RDM is the NREN. So this is RDM service, or we are connected the another service. I'm sorry, this is the last slide. So this is the future work is the Globus Connect. So Globus is very important software because Globus is many using data center or institute, so the Europe and the US. So as a result, having access to global world would be benefit for the research collaboration with institute in the regions. So we are currently conducting the research to enable access to the HPC shared storage via Globus. So we are more more collaborations, another project, but I think the Globus is one of the part of one of the services. I'm sorry, thank you very much. So this is the slide last. So my presentation is finished. Thank you very much.
Thank you, Kaneyama-san. And he also the PI of, as I mentioned, the stage 1 and the CJK collaborated a project in Northeast Asia, and very detailed describe as technically. Thank you again. And anybody question for him? Okay, thank you. I wanted to introduce the next speaker. Next speaker is the Xianwei Zhang. As a remote, he came from the Guangzhou Supercomputing Center. The Guangzhou Supercomputing Center handled and managing and developed Tenhe 1 and 2. And he also the professor of Sun Yat-sen University in Guangzhou. Professor Xianwei, are you ready? Professor Xianwei? Today's topic is multi-domain big data transfer through the supercomputing centers. I can call again. Yes, he replied me on the chat. He's not in the list. He listing. Yes, please call him. Yes, are you ready?
Yeah, I just reopened. Yeah, I will share.
Whenever
Okay, sorry.
you're ready, and go
Okay,
ahead.
sure.
And okay.
Yeah, can you guys see my shared screen?
Yes, that's okay. Go ahead.
Okay, cool. Yeah. Yeah, and thanks Jeonghoon for the organization and the invitation. And I'm very honored to give the talk. And it's a pity that I cannot meet you guys in person. And I wish we could catch up next time. And the talk is titled as data processing, management, and application support to facilitate HPC uses. I'm Shen Wei, from Sun Yat-sen University in China. And I'll first quickly introduce my affiliation and myself. And the Sun Yat-sen University, yeah, it is in Guangdong Province in southern China, and the Supercomputing Center, the National Supercomputing Center in Guangzhou, is part of belongs to the university, and it hosts two supercomputers. And about myself, I'm Xiang Wei. I'm currently the associate professor in School of Computer Science and Engineering in SYSU. And I joined 4 years ago. And before that, I was working in AMD as a researcher and engineer for 3 years. And before that, I got my PhD from University of Pittsburgh, US. And my research interests are broadly in high performance and intelligent computing, and particularly on the GPU compilation and memory system, and also on the hardware and software co-design. And okay, let's move on to the main parts. Yeah, here is the outline of the talk. I will quickly go through the projects and artifacts we have conducted and implemented. As we all know, the applications keep growing, ranging from the high performance computing, artificial intelligence, and further to the big data, or are increasing on the computation scale and the data volume. So the data-driven discovery has been the new computing paradigm, with representative examples on the conventional computational fluid dynamics, genomic analytic processing, and also on the deep learning, for example, the large language models. So data-intensive computing is very, very common. And as such, the HPC plus AI for science and engineering is being widely used and is very promising to transform the scientific computing landscape. Here, one example of the material design is called MetaGene from our center. And it basically combines the HPC and AI methods to accelerate the material research. Basically, an HPC AI framework with toolkit for material studies. It integrates online visualization, data repos, AI, and automated workflows to automate the full process. And it has constructed large-scale material genome database. And in addition, with the integrated research infrastructure, the integrated infrastructure, it is ongoing globally. And in China, we have two such ongoing projects. The first one is National Computing Power Network System, also known as Eastern Data Western Compute. Basically, it lays out a nationwide computing power network of national hubs and computing nodes. And the other one is the supercomputing interconnect. This project is to connect the powerful supercomputers across the nation. So with the trends, the geographically distributed management is strongly desired. And from the bottom figures, you can see that, yeah, the left one is within China, and the right one is the collaboration with Dr. Moon and Ken Yamasan. For this, we need a global data resource sharing and the associated storage management, basically the file system, the metadata format, and the web transfer will be heavily involved. Okay, next I will quickly talk about the data processing and management we have conducted. For the data processing and management, yeah, basically, it should support diverse data types. Because the data can be from multiple application domains, it can be of different structures. And also the scale should be pretty large to process the data in the high volume data. And also the processing life cycle should be full. It should be continuously used in the model simulation decision loops. And more importantly, the data should be fastly accessed with short access delay to support high performance computing. With this goal, we first investigated the scientific big data processing framework, because the scientific big data is quite different from the normal data. Yeah, this is to respond to the fused HPC and big data processing. For the scientific big data, the characteristics are the data is very structured, and the dimensions can be very high, and also the data interaction is heavily involved in the whole processing phase. And the existing data framework like Spark and Hadoop is not very effective in processing. So for this, we try to give easily parallel data processing framework. So for the properties, two are important. First is the description for the topological data, how to talk about to the big data frameworks. And the other one is convening the program model, means we can handle the parallel details to ease the programming burden for this. So we develop the dimensional communication primitives. Yeah, here are just the examples. And further, we should have a highly concurrent data processing capability. It means how to achieve efficient processing. Basically, we map the high data dimensions to the 1D works, and also we incorporate parallel enhancements to achieve the high concurrency. And with the prior techniques, we come up with the scientific data processing framework. And here we show some tests. We show some brief tests on the scalability and the performance. You can see that it works pretty well, and also it can support the conventional data as well. And in addition to the processing framework, we also researches on the parallel file system called Kiwook. It is a large-scale parallel file system based on the emerging heterogeneous memory, and we submitted to the L500 years ago. And it is a high-performance parallel file system, being the POSIX standard. And here is the semantic completeness testing. You can see that it passed all tests with the POSIX standards. And here is the performance studies on the access delays and the stress testing. So basically, it works well on the small files, and also the files with varying sizes, and it is functionally correcting, and performance is pretty stable in our tests. So next we can move on to the application support and data transfer, something we are actively working on. As mentioned, the systems are are diverse and they are being integrated. So it means the applications will be deployed on those distributed systems, and the migration or coordination across systems are thus strongly necessitated. For example, the scientific researches require reproducibility, and the data-centric applications need to work on multiple systems. But there's a hurdle. The software dependency becomes very complex, so it means the migration or coordination can be very challenging. So for this, the application should be deployed as a service. And in fact, yeah, this has been investigated in the scientific facilities like the LC, and APS. So it means we just deploy the application as service to continuously provide some functionalities. And toward the goal, we first investigated the container. Yeah, some speakers have just mentioned. Yeah, we call the container because it's a combined word, compiler plus container. Basically, it is a compiler assisted containers to make the black box wide. It means we want to strive for both functionally possibility and also the performance possibility. So basically, it is a record and a replay. We record the building process to standardize the build and deploy process. And then when we run on some target systems, we will replay the process and apply the system-specific optimizations to gain on the performance. And this work, yeah, it is under submission to some conference. And here is the overall design. Yeah, basically, it just models the compilation phases. So it means we develop some middle layer, yeah, to bridge the application to the underlying systems to automate and transparent the whole process. And we perform some studies on the representative HPC applications. And the results show that the performance is pretty good. It's comparable to the natively built images, and it allows faster cross-building with very little program effort. And moving further, to run large-scale and complex applications on the multiple systems, yeah, we need to chop the large application into small tasks and then coordinate the system to run the tasks are in collaboration. So for this, yeah, we studied the expressive workflow. It means we want to have a workflow system. It is expressive enough to specify the fine-grained tasks and then do some very fine-grained and customized coordination. And it can support multiple languages, means it can support the existing workflow language, and also it can adapt to multiple architecture systems. So it is an ongoing project. And actually, we have some early stage results, but I just didn't put it here. And the final one is for the data transfer. We call it a one request for all. So means instead of repeatedly retrieving data, we try to get the data just within one request. So here we just use the WebAssembly, the new language to have a Turing complete to make it a Turing complete query language for the web API. Basically, can be used in the HTTP transfer. And we developed the programming framework and also the runtime to enable the process. And the results shows that the data traffic can be significantly reduced, and the throughput and the performance can be effectively improved. And the work has been accepted into the 3W conference in Sydney. And if you are interested, you can check out the paper for more details. So basically, that's what I want to share with you guys. And finally, a quick summary. Yeah, basically, we are talking about the convergent computing on supercomputers. Yeah, the data-driven discovery and data-intensive computing. And we conducted some works on the data processing framework and management, parallel file system, and application support and the transfer. And yeah, finally, I want to just to share one small artifact. And I think it can be very interesting because it's a new one from our group, yeah, developed by my students. And it basically integrates all the prior techniques I just introduced. It developed an education platform for the course teaching. Basically, the compiler course the practical platform with supercomputing and the large language model, the DeepSeek. Yeah, you can see that yeah, we can do very smart chatting, coding, and compiling inside the platform with just a web page. And if you are curious, yeah, you can check out the website to learn more. Yeah, basically that's all my stuff. Yeah, thank you guys.
Thank you, Professor Xianwei. Anybody question about that? I think he did a very big job, so very well. Yes,
yeah, just quickly, yeah, it is the many projects we have conducted.
Andrew here. I was just interested in the results you've obtained out of DeepSeek. Which size model are you running, and what level of quantization?
You mean which part?
DeepSeek. The one when you're showing on your slide now. Which DeepSeek model are you using, and what quantization level?
I didn't quite get that.
So are you using DeepSeek R1? And
oh yeah, that's right. Yeah, DeepSeek R1. That's right. Yeah, but it's a small size. It is 32B, and because we just used for the course teaching for 200 students. Yeah. So it's a locally deployed DeepSeek R1.
Excellent. Thank you.
Yep.
Okay. Thank you again, Professor Xianwei.
Yeah. Thanks, Dr. Boone. Thank you, guys.
Meet again.
Okay, yeah.
Thank you.
I wish. Yeah. Okay.
I want to introduce the next speaker. That is the final speaker, Dr. Elif Naz Wenger Aksoy. She came from the Beykoz Institute of Life Science and Biotechnology in Istanbul. And she talking about is bioinformatics and related HPC works. Dr. Elif, are you there?
Yes, I'm here.
Okay. Thank you for joining, and whenever you're ready, and go ahead.
Okay. Hello, everyone. My name is Elif Naz Bingöl Aksoy. I'm here on behalf of Professor Asif Khan. I'm a postdoc researcher in Beykoz Institute of Life Sciences and Biotechnology in Istanbul, Turkey. It's a pleasure to be here at 59th APAN to discuss a topic that is transforming the way we approach biological research. Today, we'll explore how HPC is accelerating discoveries in genomics, drug development, AI-driven biology, and even pandemic response. Let's start with the basics. What is bioinformatics, and why does it need HPC? Bioinformatics is where biology meets computing. It's an interdisciplinary field that applies computational tools to analyze biological data. It brings together concepts from computer science, mathematics, physics, and biology to interpret massive amounts of biological data. Modern biological research isn't just about collecting data, it's about making sense of it in real time. So bioinformatics wouldn't be here where it is today without the power of HPC. It enables large-scale data processing, such as assembling and annotating genomes, which would be impossible on standard computers. A single human genome produces over 200 gigabytes of raw data. So imagine handling thousands or even millions of genomes. In omics sciences, genomics, transcriptomics, proteomics, we deal with high-dimensional data requiring complex computational analysis. HPC enables us to process, store, and analyze this data efficiently. High-speed genome sequencing and variant detection is very essential for personalized medicine. So this is one of the areas HPC makes a difference. So let's put this into perspective in a real-world example. The Human Genome Project, completed in 2003, it was one of the most ambitious scientific undertakings in history. It took 13 years and cost around $3 billion to sequence the first human genome. At the time, they simply didn't have the computational power to do it faster. So thanks to HPC, today we can sequence a full human genome in a few hours for about $1,000. That's a massive reduction in both time and cost, making personalized genomics and precision medicine a reality. But genomics is just one piece of the puzzle. Let's move on how HPC is helping in drug discovery. It is one of the most expensive and time-consuming areas of biomedical research. On average, it takes over a decade and billions of dollars to bring a new drug to market. So how does HPC help? MD simulations allow us to study how drug molecules interact with proteins at the atomic level. By using HPC, we can run thousands of AI-driven docking simulations in a fraction of the time. This speeds up virtual screening and helps identify promising drug candidates faster. But drug discovery isn't only field benefiting from AI. Artificial intelligence and machine learning are revolutionizing bioinformatics by automating complex analysis. For example, deep learning models like AlphaFold2 are predicting protein structures with remarkable accuracy. AI is also being used to analyze genetic markers for disease susceptibility, which helps with early diagnosis and personalized treatments. And NLP is being applied to extract insights from vast amounts of biological research data, which links genes to diseases. So let's take a closer look to AlphaFold2, one of the biggest breakthroughs in structural biology. The protein folding has been one of the biggest challenges in biology for decades. The Leventhal paradox suggests that a protein could theoretically take longer than the age of the universe to fold. So using AI in HPC, AlphaFold2 solved this. It predicts protein structures with atomic level accuracy. Its attention-based neural network architecture allows it to learn from evolutionary and structural data. The training AlphaFold2 required 16 TPU cores, so it reduced the computation time of folding simulations from months to hours. But like any technology, it has its limitations. So AlphaFold predicts static structures, but it doesn't fully capture conformational changes. So post-translational modifications are not yet accurately modeled. And so in the future, the integration of quantum simulations with AI could enable even more powerful predictions. And this could also help us model real-time protein dynamics with unprecedented accuracy. So speaking of AI innovations, let's move on to BioMU1, which is a deep learning model developed by Microsoft Research. It can generate thousands of protein structures per hour on a single GPU. So it's 10,000 to 100,000 times faster than traditional molecular dynamics simulations. It is trained on AlphaFold database, so it has AlphaFold biases and limitations. It also trained on MD simulation data and protein stability datasets. So this is taking AI-driven structural biology to the next level. Now, let's discuss how HPC has played a critical role in pandemic response. HPC has been instrumental in real-time viral tracking and metagenomic analysis. During COVID-19 pandemic, researchers used HPC to sequence and analyze virus mutations in real time. So this allowed for rapid variant tracking and informed public health decisions. HPC has also been critical in vaccine development, which was very important. They analyzed the virus's genome within days, which speed up the vaccine design. Pfizer, BioNTech, and Moderna used HPC to computationally model mRNA vaccine candidates. HPC also helped in drug repurposing, reducing the time required for clinical trials. So this is a real-world example of how HPC directly impacts global health. So we can all agree on HPC is revolutionizing bioinformatics, making large-scale data analysis, AI-driven discoveries, and real-time simulations possible. So with advancements in AI, quantum computing, and HPC, the future of bioinformatics is evolving rapidly. The coming years will bring several breakthroughs that not only accelerate research, but redefine how we approach biology and medicine at a computational level. Thank you for your time.
Thank you, Dr. Elif. The Turkey time is early morning, around the 6 and the 6:30, and you wake up really early. And she take over this Asif Khan's presentations. So thank you, really thank you. I want to ask something. You mentioned before there's AlphaFold 2 and mentioned the integrated AI and quantum computing. I want to focus on the quantum computing. Is it possible to near future or far future?
I think it will be near future.
Oh, really?
Because all the advances are exponential, and the advancements in quantum computing will definitely be integrated to bioinformatics soon.
Okay. Okay, anybody question for her? Okay, thank you, Dr. Elif. See you again.
Thank you for having me.
Yes, I want to wrap up this APRP working group session 2, and in the afternoon, the APRP working group session 3, and it would be closed. Sorry about that. And we need the discussion with the project PIs. So And I realized this the several the presentations and their contents and the explanation about their jobs and always the finally need for the HPC power. The HPC power is the big indicator for the advance of the country and national competitions. And anyway, and thank you again. Join our session. Have a good lunch. See you again. Thank you, staff. Okay.